So unfortunately, I won't have time for the very last topic. But in the last lecture, I want to tell you a number of things about the challenge of UV completion in general, and how to start thinking about UV completion from the bottom up. Many of the things that I'll say are sort of common lore. They're just gathering some basic things in a sort of coherent way. But towards the end of the talk, if I get to it, using this sort of strategy to try to determine UV completions of theories like gravity is work that I've been doing for a while with Yutin Huang and one of his students. And depending on how much progress we make, it should appear sometime. Okay, so first a few general things. Let me just remind you of the issues where the issue of UV completion hit us in a very familiar way in particle physics, and it first arose in a way that people cared about a lot in the context of the weak interactions, right? So what do we mean UV completion? We know that we have massless particles, low energy particles, in some approximation they're massless. We know they have scattering amplitudes. We know how to calculate the scattering amplitudes, characterize them from symmetries, other arguments, things that we hear about from Cliff. And that's the purpose of those things, is to make sure that the amplitudes have the correct properties at long distances, that they have the right singularities, the right factorization properties in order to be local and unitary at long distances. But these very amplitudes, when we compute in gravity, for example, the amplitudes blow up as we go to high energies, right? And so we have the famous problem that despite the fact that we're assuming some weak coupling in doing all these calculations, that breaks down. As we go to very, very high energies, the amplitudes can't become bigger than 1, the probabilities can't be bigger than 1, so something new has got to happen. And of course, famously, that problem is there in gravity. But let's back up and think about how we ran into it in particle physics. We first ran into it in the context of the weak interactions, right? When we have the weak interactions, the low energy amplitude, the 2 to 2 low energy amplitude, looks like some scale 1 over m squared, and it goes like s. So it grows with energy. And when s becomes of order the scale m squared, the amplitude gets bigger than 1. Okay? So what idea did people have? Well, it's always possible that what the physical actual amplitude does is it gets really big, and then some totally new dynamics takes over. Things get melt into completely different degrees of freedom, and so on. That's always possible. But what people did, first largely because it's the only thing they could do more concretely, and then it also happened to be true in nature, is that the UV completion was weakly coupled, so that the actual physical amplitudes never became large. Right? They started growing, but before the scale m, something new happened. Before the scale m, something new happened, and in the new theory, the high energy amplitudes became smaller, right? Or they were bounded by a constant at least. Okay, now here of course we know in the weak interactions we introduced the w. So we opened up that vertex and we introduced a w, and this became g squared over mw squared. And instead of s, we have s over 1 minus s over mw squared. Okay, so we could write it like that. Right? So I write it like this instead of the more familiar g squared over s minus mw squared, okay, to emphasize that you could have guessed this. A way that you could have guessed this, even without thinking there's a w there and so on, is you could say, look, I just want to write down an amplitude that makes sense. Don't bother me with where it comes from, Lagrangians, this, that. I just want to write down an amplitude that makes sense. So if it looks like 1 over m squared s, then I'm going to just multiply it by a factor that's 1 when s is small and goes down to 0 when s is big. So I'll multiply it by 1 over 1 minus s over some scale that I'll call mw squared. Okay? All right. So this is now an amplitude that matches the right answer at low energies and is fine at high energies. No problem. Okay, very good. So, and in fact, we can work out, but now from the previous lecture, you remember what the rules are supposed to be when you have, what the rules are supposed to be when you have amplitudes that have only poles, right? If they have only poles, so we're assuming there's a weak coupling here, so that scale MW is smaller than the scale capital M, and that's reflecting the fact that there's a weak coupling G in town, right? So the amplitude only has poles, but it's telling us there's another particle in the world, right? And if we did this really carefully, I actually didn't do it carefully here. I didn't do the correct amplitude. What I did here is actually not the W UV completion of this four fermion operator, but a UV completion if I integrate out of a scalar. Okay? And you know that that's what I did because from the rules of the previous lecture, right? I know what I'm getting. When I go on the pole in the S channel, right, I have to be able to interpret the numerator as a sum over partial waves, okay? The Gegenbauer polynomials of cosine theta. In this case, it's very simple because it's just a constant. So I'm just exchanging a scalar, okay? So in fact, this is UV completion that ends up being false. It's not the correct completion of the four Fermi theory, but just as a toy. I leave it as a little exercise for you to do it for the right answer, okay? Just take the right answer. It's very simple, and the right answer, instead of the S there, I mean, you would have I won't do it for you, okay? So do it. What you'll find is that upstairs you'll have a single power of T. And that's what's telling you there's a spin 1 particle that's being exchanged, okay? And so you discover that there's a W there, okay? So that's what happened there. But then we had to keep going. Now we have this massive spin 1 particle. Now we took the massive spin 1 particle and we scatter the massive spin 1 particle together, and we find the longitudinal components of that grow, right? So let's now go to that one. Okay, so that one I remember the formulas off by heart. If we do that one, then there too, if I think about the longitudinal components, we know that it's governed by a nonlinear sigma model, although you could discover that from this amplitude's perspective as well. But in any case, one way or another, what you discover is that if you have these things have flavor indices, but if we order them in some flavor ordering, that partial amplitude goes like negative S, negative T, 1 over F squared. Okay? That's what the pi scattering amplitude looks like in the 1, 2, in the channel where it's proportional to trace TA1, TA2, TA3, TA4. Right? So again, this blows up as you go to very high energies. Right? And again, let me do the same thing. I don't want to care Mexican hats, blah, blah. Gives a crap. I want to fix this amplitude. So, dumbest thing I can do. Negative S over 1 minus S over M squared. Negative T over plus negative T over 1 minus T over M squared. Okay, there's an ST symmetry that I don't want to break here, so I do that. Okay, that is an amplitude, which is, again, it's fine in the UV, right? Now we have to check, is it okay on the pole? Okay, and again, on the residue of the pole, what do I get? On the residue of the pole, S is equal to M squared, right? So because there's a minus sign there, that kills the minus sign there. And the residue on the pole, the residue on S goes to M squared is equal to just M squared over F squared. Just a constant again. Right? So that tells me that there's a scalar particle being exchanged here with mass m. And if m is parametrically smaller than f, this amplitude never becomes large. Okay? Similarly in the T channel. So what is this called? This is called the Higgs. Right? So we wanted to UV complete the nonlinear sigma model amplitudes, and we just did it. Okay? Just wrote it down. And now, this is, certainly at the classical level, this is no better, no worse than writing a whole Lagrangian, Mexican hat, this, that, the other, right? It has exactly the same content, right? Well, you'd do a little more. You'd want to show that this new particle scatters in some sensible way and so on. You have to do a little bit more work. But I just want to point out this sort of strategy of just trying to change the formula in this very simple way where you only have poles. Okay, so you have an approximation, you imagine there's an underlying weak coupling, and so you try to take the low energy amplitude, which has things that are blowing up, and then you try to fix it in a way that only introduces poles. Okay, nothing more complicated, only poles, so that the high energy amplitude is well behaved. And you have to then check, though, once you've introduced the poles, that on the residue of the poles, you can consistently interpret it as exchanging particles. Okay? So that's what I want to just spend a little bit of time telling you what the precise rules are. Okay? And then we're going to switch to a different set of theories, namely theories like gravity, or Yang-Mills theory, or Phi Cube Theory. Okay? These are theories that, depending on the number of dimensions you're in, also need UV completion. Gravity in any number of dimensions, right? Yang-Mills is okay in 4 dimensions, but it needs UV completion in 5 dimensions. Phi cubed is okay in up to 6 dimensions. It needs UV completion in 7 dimensions. And if you're a Wilsonian person who thinks that the only thing that matters is the dimensionality of the coupling constants and nothing else, there doesn't seem to be a big difference between, the nonlinear sigma model and gravity. They both have coupling constants with the same units of dimension. They both have amplitudes that grow like energy squared as you go to high energy. So why is it that one of these theories is relatively easy to UV complete, and in lots and lots of ways, right? The nonlinear sigma model, even if I want a weakly coupled UV complete it, never mind, we can UV complete into QCD. That's a strongly coupled completion. Never mind that one. I just want to do weakly coupled completions, and it's a dime a dozen. I can have 1 Higgs. By the way, this is highly non-unique. I can add 1 of these guys. I can have 12 poles, and those correspond to having 1 Higgs or 12 Higgses. Okay, it's many, many different ways of doing it. So it's not very constrained. Okay, so you need experiments to go see what's actually realized in nature, if any of these things, right? But so some theories are like that. The nonlinear sigma model is like that. These sort of fancy theories that we ran into in the 20th century, the weak interactions, the nonlinear sigma model, these are the things which we ran into, but which could also UV completed within 30 years. Okay? And yet, these other theories, they look basically the same dimensionality coupling constant, but Newton knew about them. Those are the things that we are still struggling with today. Right? So why is that? Why are some theories easy to UV complete, and some theories, like gravity, we think, it's only string theory can UV complete them, or something like that. At least, sociologically, you think it's the only game in town, the only thing we know that can possibly complete it. Why do some of these theories need high drama, and some of them are relatively easier to do? Okay? So that's, after we set down the rules in a second, that's the first issue that I want to explore. But let me tell you what the answer is ahead of time, because it's a cool answer. The answer is that theories where the low energy amplitude, for 2 to 2 scattering, is already local, is already coming from short distance physics. In other words, where there is no 3 particle amplitude, there's only a 4 particle amplitude to begin with. So it's a contact interaction. Where the low energy amplitude is already a polynomial, theories like that can be UV completed. Well, let me say it in a way that's independent of the dimensionality. Okay? Let's say you have a low energy amplitude that grows as some power of the energy. High energy fixed angle, the sort of standard thing that we talk about when we talk about high energy amplitude. Let's say you have something that's growing as some power of the energy. And let's say your purpose in life is to fix it in the UV. Maybe it doesn't need fixing. Like Yang-Mills in 4 dimensions, the amplitudes go like a constant at high energies, right? At fixed angle, the coupling is dimensionless. A constant is fine in 4 dimensions. It's not fine in 5 dimensions. Amplitudes in 5 dimensions have got to go like 1 over energy in order to be okay, right? But it just goes like a constant. Let's say your mission in life is to improve the high energy behavior relative to the low energy one. That's all you want to do. Make it better. Okay? Sometimes you need to, sometimes you don't. But let's say you just want to make it better. That way we can not talk about the dimensionality for most of the rest of the argument. Okay? Then the claim is going to be, and we'll see this, the claim is going to be that any theory that starts with a polynomial interaction, it goes like S to some power, that it's possible with a finite number of particles, finite number of poles, to UV improve it by 1 power of S. Okay? Okay? Now, that happens to be good enough for all the examples that we know. That's exactly what we needed in all these examples. Right? On the other hand, theories where the 2 to 2 scattering has a pole in it already because there's a massless particle exchange. right? So there's a 3-particle amplitude, so there's a long-distance piece of the scattering. It's not, something we only learn about at very short distances. We get to measure it at very long distances. Things where there's a long-range force, where the 2-to-2 scattering has an infrared pole in it. Any such theory, it is impossible to UV improve with a finite number of particles and with a finite number of particles. Okay? Any such theory needs an infinite number of particles and an infinite tower of spins. Not just infinitely many particles, but an infinite tower of spins. And in a little bit more detail, it has to have something like the famous duality of string theory, that you can expand it in the S channel in poles or the T channel in poles, but not both. Okay? All of those things are things that just follow on very general, very simple grounds. Okay? And that's the dramatic difference between the two kinds of theories. So it's really interesting. The theories that have infrared poles, which are exactly the ones, for that reason, that could have been discovered 400 years ago, because they affect long-distance physics and you don't need fancy things like radioactivity and colliders to learn about them. Those are exactly the things that are the most mysterious, that can't be completed in a garden variety way with a finite number of particles and a finite number of poles. Meanwhile, the things that are genuinely short-distance phenomena to begin with can be fixed, at least by this one power of S. Okay, so and absolutely crucial to this entire discussion, in a sense, I mean, there's a number of important points, but by far the thing with the biggest teeth in it is unitarity. Is the requirement that when you sit on a pole in the S channel, that the numerator should be a sum over the Gegenbauers with positive coefficients. That positivity is the entire story, almost the entire story, tremendously non-trivial. If you allow yourself to put minus signs there, you can do anything you want. Okay? And we know that. If you allow yourselves to add ghosts to the theory, just from the Lagrangian point of view, it is trivial to UV complete things. Okay? But if you don't allow yourself to do that, it's hard from the Lagrangian, and we can see more directly that it's hard directly from trying to write down an amplitude. Maybe because I don't have an infinite amount of time, instead of being super duper systematic, let me already give you a flavor for why it is challenging. Okay? And we actually see a little avatar of this already in this example that worked. Remember I told you the low energy amplitude was negative S, negative T. Okay? Now, why did I remember that there was a minus sign in front of that negative S, negative T? It's because, I mean, we know that this example works, right? So this is actually what I get from the Higgs. But suppose that the low energy amplitude was positive S, positive T. Okay? Say it had the opposite sign. Then I couldn't do it. See, then I can't UV complete this guy. Because if I try to do it, well, if I try to do the same game, now what is the problem? The problem is that the residue on S equals m squared is negative, not positive. Right?
Why can't you multiply by a negative denominator?
Very good. Well, even if I put a plus sign there?
And then make the 1 minus.
Oh, well, putting the minus is 1. Okay? But you could do this. Okay? You could do this. This is okay. What's the problem with this? It's a tachyon, right? The pole isn't at positive m squared. Okay? So that, I should have said that. Tacitly, I'm assuming, of course, all the poles are at positive m squared. Okay? So if you assume the poles are at positive m squared, then you couldn't do it with the plus sign. That's really interesting. It seems to tell you that from sort of unitarity or general principles, some signs of these contact operators are actually fixed. Okay? And you can see that just from the low energy theory. Okay, and in fact, that's right. So, and this is a more general statement that even though it's not totally obvious from general effective field theory considerations, that if you have higher dimension operators, some of these higher dimension operators have fixed signs. And in fact, the model independent way of saying the statement, for example, if you have a single scalar field, you have an amplitude for a single scalar. This wasn't the single scalar. There were some color flavor factors that I pulled out. But if the amplitude for a single scalar field, so it has to be symmetric in ST and U, then it could start with it could have a piece that goes like S squared plus T squared plus U squared, and the coefficient of that has got to be strictly positive. Okay? And if it's negative, you can't possibly be compatible with unitarity in the UV. But you see, here it didn't matter so much because there's no God-given. We didn't know what the sign of these contact interactions had to be to begin with. Okay?
Yeah, we're not
Okay.
saying that the UV completion depends on the attraction or the
No. This is just. I mean, this is just telling. In this case, you were learning whether it's attractive or repulsive, but that's more an output than an input. Okay, so let's now contrast it with another example. Let's say we have Phi Cube Theory. Okay, so what is the amplitude for Phi Cube Theory? It's mu squared. If the coupling is mu, 1 over s plus 1 over t plus 1 over u. Okay? And now let's say I want to UV improve this guy. Right? Again, in 4 dimensions I don't need to, but in 7 dimensions I need to. So just for the sake of argument, I want to UV improve this guy. Well, let's try some of the same things. So if I mu squared, let's say I put a 1 over s, 1 minus s over m squared, plus 1 over t, 1 minus t over m squared, okay? 1 over u, just to start with an example. This trick works so well. Now what's wrong with this example? What's wrong is that you have a pole at s equals 0. The pole at s equals 0 involves the massless particles you know are there, and its residue must be positive, right? Mu squared is positive, good. But once its residue is positive, it is impossible for the residue of the other guy to be positive, right? And in fact, it's negative. So the reason we have an extra constraint is that in the case where we have massless particles, the signs of the low energy amplitudes are fixed already from the presence of the light particles. And so then we have no freedom to adjust them to fix up something. Okay? And in fact, they're always in conflict with what happens up there. Let's say you write down arbitrary complicated polynomials upstairs, downstairs. But let's just keep it in this factorized form just for a second. Okay, so it's just a function of s plus t plus u. Guaranteed that somewhere there's a minus sign. Why? Because the sum of all the residues have got to vanish by Cauchy's theorem. Okay? Because the whole purpose of all those things is to make the amplitude die faster than 1 over s as you go to infinity. So if you sum over all the residues, you have to get 0. So since one of them is plus, there must be some minus sign somewhere. Okay? So that's now that's in this very special example, but this ends up being a very general feature. Okay? And with a really very small amount of work, you can prove the statement that I made. So I'll make the statement a little bit more sharply after spending a tiny bit more time on the rules. Okay.
So it seems like you're using the UV completion to easier low energy theory, not going the other way.
Well, no, you could say it the other way. You could say that if someone told you my low energy theory had plus signs, you would work and you'd say, I'm sorry, your low energy theory is completely inconsistent. It can't come from any consistent ultraviolet theory. That's interesting that you can make a claim like that. Okay, that's a little bit more than what Wilson tells you that you're allowed to do. Okay, but constraints like that, more constraints of this sort have been found over the years. This is just a very simple example where you can see it in action, just assuming weak coupling, but it's a more general statement. Okay, so but is it clear from that example? At least, did you have a sense for what's challenging, right? Another way of saying the challenge is that with a finite number of particles, you are trying to fix up the UV. You're trying to change what the fixed angle high energy scattering looks like, right? But if you make S humongous, as big as you want, you think I'm deep in the regime where I have no idea what's going on. S is huge. But if I make S enormous, but make T very close to 0, as I hit exactly 0, I know exactly what the numerator's got to be, right? It has to be the residue that's guaranteed from low energy physics. Okay? So if you want to change, with a finite number of particles, you want to change the fixed angle behavior, which are just polynomials, right? If you're going to change it, it is impossible to change it keeping all the signs positive without messing up the residue at t equals 0. At t equals 0, but huge S. All right? Yes? QED is completely fine. If you want to, exactly the same thing is true. If you try to improve the high energy behavior, of the amplitudes compared to what we get just with photons. We can't do it with a finite number of particles and a finite number of poles. It's true for Yang-Mills theory, Phi Cube Theory, gravity. From this point of view, it has nothing to do with diffeomorphisms and black holes and gravity, special, nothing. It's really a more generic feature about theories with long-range forces. Okay? When you have massless particles and you have three-point interactions so that the four-particle amplitude has poles already, infrared poles, then you can't make it better at high energy. It's just that in QED in 4 dimensions, we don't care because it's a perfectly weakly coupled theory already. If in 5 dimensions, we would care. And it's interesting. You ask, what do we know any theories that UV complete? Yang-Mills, gravity, Phi Cube Theory. The answer in all cases is string amplitudes. String theory is the only theory that we know of that gives us amplitudes that are well behaved. Okay? I'm about to turn that towards the end of the lecture into a sharp mathematical conjecture. Okay? So there's a very well-posed statement about the uniqueness of the amplitudes you get from string theory, and I will state what it is. Okay? But it's a problem you can hand a mathematician, and they can, in principle, prove it. There's no wiggle room in it, and you'll see what it is. Yeah, we'll get there. Okay? Yes.
Sorry, what's the reason you can't redefine f squared to be negative such that this problem seems to go away? Like or your coupling, whatever it is, you can make it go.
I mean, you can do whatever you want. The actual amplitude is a number, right? Yes. The amplitude is an actual number, and you can define anything to be anything you want, but the actual numerical value of the residue at the pole has got to be a positive number. Okay, so if you, yeah.
Okay, I see.
Okay. Okay, yes?
Why does the residue need to be?
That's what we saw from the previous lecture. From the previous lecture, we saw that the residue on a pole has to be interpreted as an exchange of some particles of some spin. And we said ahead of time what it has to look like. It's those g squareds, those coupling squareds, times the Gegenbauer polynomials, right? We have not yet seen fancy Gegenbauer polynomials because all these residues so far have been a constant, which just correspond to spin 0. In a little bit, we'll see fancier ones, okay? All right, any more questions? All right, so let's talk about the rules for weakly coupled UV completion. And this is actually, I mean, it's a subject that needs a few more lectures. So some of the things I'll say a little quickly, but I'll give some physical motivations for them. So, number one, we want an amplitude with only poles. And when S, T, U, etc. is much, much smaller than some high energy scale, let's call it 1 in some units, right? Oh, let me keep some scale, some high scale, m squared. The amplitudes reduce to the correct low energy amplitudes. So that's the first obvious things. And we want it to be bounded by a small constant for high energy fixed angle. Okay, so that's the most obvious. So high energy fixed angle means S, T, everything is large, but S over T fixed to be something of order 1, fixed. Okay? Okay? Now, 2. Let's immediately dispose of an apparently totally trivial way of solving these problems. Okay, I said that the amplitude should only have poles for its singularities, but why don't I just do this? Let's take the Phi Cube Theory example. I had 1 over S plus 1 over T plus 1 over U. And here, e to the minus S over m squared plus T plus U. Okay, and oops, well that's 0. So let me, and anyway, even if it wasn't 0, S, T, and U can sometimes be negative. So here, let me make my life better. Let me just square everything. Okay? Okay? So I'm just multiplying with an exponential factor in front, just whomping the amplitude when S, T, and U get large compared to m squared. Okay? Beautifully, amplitudes are small, no problem. Okay, now, this might seem like cheating to you. Okay? Just for its sheer stupidity and its sheer easiness of doing it, and how totally unconstrained it is, right? Because I could have put the 6th powers, I could put anything I want there, right? But what's actually wrong with it? So, well, the poles just at ST and U is 0. The usual poles. It doesn't have any other poles. It has an essential singularity and infinity. Okay, but what the singularities are infinity, well, this is related to the subject. But you can't say that the amplitudes have got to be bounded everywhere at infinity. For example, even string theory amplitudes aren't bounded everywhere. They die exponentially in the physical region, but they blow up exponentially away from the physical region. Okay, so it's not quite as cut and dry as that. Now, in order to explain what is wrong with this, what's wrong with it is that these things violate causality. They cannot be causal. Okay? And the fingerprint of that is that if you're an approximation where you hold, let's say, t fixed, and you make s huge, s goes to infinity, then causality implies, in fact, implies a little bit more than this, but it certainly implies that the amplitude is polynomially bounded in S. Okay? Slightly more detail. It's polynomially bounded. If you have a pole 1 over t, it's polynomially bounded by s to the 1. Okay? But that's a little more detail that we won't need for what I'm talking about. What I'll be talking about. In any case, if you just believe this for a second, obviously these idiot things where you multiply by e to the minus s squared plus e squared plus u squared won't satisfy that. Okay? Because if at fixed t, they're certainly not polynomially bounded in S, in often the complex S-plane. Now, instead of giving some more formal reasons why this is true, there's some very nice physical pictures involving shock waves and other things like that. There's many, many reasons why this is true. These are very old arguments that people have understood for a long time. They're very similar to the requirements for not being able to go faster than the speed of light, just in optics. Okay, these are the most primitive restrictions on the most primitive aspects of the analytic structure of propagators and amplitudes that come from causality. But let me give you a sort of physical picture that this is associated with, just to make it a little bit more plausible. You see, let's just forget about all this. You might think, here's a very easy way to UV complete. Let's just put a form factor, right? That's what we're doing. Let's just put a form factor. We just cut everything off. What's wrong with that? There's nothing wrong, naively, with the idea of putting a big form factor in Euclidean space. Because that's in Euclidean space, there's a clean meaning of what short distance is and what long distance is. There's only one notion of distance. It's always positive. And you can say big and small, and you can know the invariant difference between them. But in Minkowski space, this is more confusing. Because distance can be positive, it can be negative, it can be 0. So when you have a 0 distance, or the points close to each other, or they can be arbitrarily separated on the light cone. Right? And so if you attempt to put willy-nilly some cutoffs directly in Minkowski space, then you are screwed, because making things a little non-local in space will inevitably make them a little non-local and acausal in time. Okay? And if you want to smoothly cap things off in space, then they'll be smooth in time. But smooth in time means forward and backward. What you want is for it to be sharp in time. Nothing forward, only backwards, let's say. But you can't be sharp in time if you have a smooth cutoff in space. That's the intuition for why you can't just willy-nilly throw form factors in. And if you say, that sounds like a good physical argument, but let me do something technical, and surely it'll work, I'll just go to Euclidean space first. I'll go to Euclidean space, I'll put form factors, everything is great, e to the minus p squareds everywhere, e to the box in front of the kinetic term, all these things, all the propagators dead, everything is great. I'm done. All the correlation functions are great. Sue me, right? What's wrong? Well, what's wrong is if you try to continue that back to Minkowski space, nobody guarantees that you get a causal theory, and you don't. The usual arguments about getting a causal theory using analytic continuation assume that you can throw out contributions at infinity and all these integrations going back and forth from momentum space to position space, and precisely when you don't have this polynomial boundedness, those arguments break down. Okay, so both from this physical perspective that it's hard to put form factors in Lorentzian signature, right? I've said it many times in these lectures, but it's very weird that the world has both quantum mechanics and relativity. Relativity is a very weird thing. And it makes it very hard to just imagine that you put some kind of smooth cutoff in Minkowski space. And even if you do it in Euclidean space, you find that you're screwed when you come back to Minkowski space. So this is the second requirement. It's a very primitive requirement of causality that fixed T, the amplitude is polynomially bounded in S. And finally, we have unitarity. And unitarity tells us that on a pole, as S goes to m squared, the residue has to equal a sum over the Gegenbauer polynomials in if you're in d spatial dimensions of cosine theta with positive coefficients. These coefficients C, CS, these coefficients CS have got to be strictly positive. Right. That's it. So, if you have, so now let's look at some examples. Oh shoot! Well, let me leave that up. So if you manage to find a function, it's a very simple problem, simple-looking problem. You just want a function of two measly variables, s and t, and it needs to satisfy 1, 2, and 3. And if you do it, you have a candidate for a theory that UV completes something. All right. Yes?
Regarding the first rule, I understand that if, say, the new physics can appear in the tree diagram.
This is assuming some version of tree diagrams. Okay, so I'm assuming there's a weak coupling. Okay,
But if I
that.
want to be completely sometimes losing that when new physics will only appear at the loop.
No. When you have a weakly coupled theory, when you go far enough, all the physics occurs at tree level. Okay, so let me give you an example. Let's say you want to do Euler-Heisenberg. Okay, so you want to have photon scattering, and that's something that we know we can UV complete in a weakly coupled theory, but it involves electrons that running around a loop. And in fact, it follows a rule that I told you. I told you that with only poles, you can only improve the amplitude by 1 power of s. If you take Euler-Heisenberg, the low energy amplitude grows like energy to the fourth. And so by my rules, you can only improve it down to energy squared. Okay? So it's still not good enough. And yet, oh, sure, I can do it. I can do it with an electron running around the loop. That's fine. So that means that this particular amplitude, the photon amplitude, does not have poles in leading approximation. It has a branch cut, right? Because you have something at loop level. But there's new particles there, the electron. Now look at the amplitude involving the electron. The amplitudes involving the electron have poles. So if the amplitude that you start with doesn't have poles, but the theory is weakly coupled, it has a branch cut. That means there's new particles. You take those particles, you keep looking at the amplitude for all of them, and in the level of approximation you're talking about, you'll eventually end up with somebody that has poles. May not be the guys that you started with. Okay? Any other questions? All right. So, so what we just saw with what we just saw with the Phi Cube theory, we saw how easy it was to satisfy 1 and 2. Totally trivial, right? In the examples that we did, we multiplied by 1 over 1 minus s and so on. 1 and 2 were easily satisfied, right? It's 3 that's really hard. It's 3 that's really, really hard. And in fact, you saw a flavor of it with the Phi cubed example, and for reasons of time, I won't go through a formal proof, but it's an easy enough exercise that you can do, that this is true for any theory that has these infrared poles. Any theory that has an infinitive poles, precisely because of 3, it is impossible to complete it with a finite number of particles and a finite number of poles. Okay? Now, let me illustrate this with an example. Let's look at 2 amplitudes, gravity amplitude and a Yang-Mills amplitude. And now, just so I don't have angle and square brackets all over the place here, and this is just for some convenience, I'm going to imagine that I'm talking about a theory of maximal supersymmetry. You don't need to know anything about this. Okay, but just to say that all the information about helicities and things like this is buried in some version, supersymmetric version of momentum conservation. And when you have that, the full 2 to 2 gravity amplitude looks like this. Okay, looks like 1 over s times t times u. If you extract components out, if you extract a component amplitude, let's say 1 minus, 2 minus, 3 plus, 4 plus, what Cliff will derive for you tomorrow, I imagine, is that this would contain as a component angle bracket 1, 2, square bracket 3, 4 to the 4th over s times t times u. Okay? And that's if you pick these components. You can pick dilitons, you can pick gravitinos, all sorts of stuff. It just has different angle bracket stuff that come out, and it's all nicely packaged in some supersymmetric object. Okay? Meanwhile, a Yang-Mills amplitude, or again, if I look at a color-ordered piece of a Yang-Mills amplitude, looks so for example, just going back here, if I pick dilitons out, if I pick scalars out of here, then instead what I would get is, let's say, s to the 4th over stu. Okay, that's what I would get if I took some scalars out. So that would be s cubed over tu. Right? What I want you to notice from this, let's say from that s cubed over tu, you'll notice that here, in this answer, it looks like a product of st and u. That looks strange because you think that it's coming from an exchange of a particle in the s and the t in the u channels. And it's true that if you look at every component amplitude can indeed be interpreted as a sum of pieces in different channels, st and u channels. Just a trivial exercise, look at s cubed over tu, and you can break that up into something over t plus something over u. Okay? But it's an interesting fact that the fully supersymmetric expression does not break up into the sum of poles in the st and the u channels. And this is the world's fastest proof that there's no such thing as off-shell superspace with maximal supersymmetry. Okay? If there was such a thing as fully off-shell superspace with maximal supersymmetry, there would be some formula in some ersatz theory whose Feynman diagrams are maximally supersymmetric, where every term had the delta function for momentum and supermomentum conservation, and you should be able to express the answer by pulling out both of these delta functions as something over s plus something over t plus something over u, and that's impossible. It's a product down there. Okay? All right, that's just a little amusement. The analog for Yang-Mills, sorry, this is delta 16. The analog for Yang-Mills is delta 4 of momentum, delta 8 of q, over s times t. All right? All right, so these are really simple formulas. And let's try the same thing. Okay, let's, we'll just see as a very, very simple example here. Let's try some of the same games. For example, here it looks like there's a product of st and u. So let's say y couldn't have been 1 over stu. And then I'll write down with all the deltas out in front. But let's just look at this part. 1 over 1 minus s over m squared. Let me keep it like a product. I could do many other things, but let's just start with this as an example. OK, what's wrong with this? Yes? That q is some, in a normal theory, you have translational invariance, and so we have momentum conservation. In a supersymmetric theory, we also have supercharges. Okay, and so there's also so just like we have delta functions for momentum conservation, we have delta functions that enforce supermomentum conservation. Okay, and so I haven't explained what it is. All I wanted to say, even without writing this, maybe what I could have said is that every single formula for every component is this universal factor 1 over s times t times u times something upstairs made out of angle and square brackets. Okay, and it's just that it has a very nice underlying supersymmetric origin. Okay, I'm doing this just so you see there's something natural about this product structure, because I'm going to use that to motivate a little ansatz in a moment. Well, let's say we do something like this. Now, this is something I told you that's guaranteed not to work, right? But here it's particularly instructive. It's particularly horrible what happens. Let's say I sit on a pole in the S channel. It isn't even a polynomial in T. The residue isn't even a polynomial in T, right? It's a 1 over 1 minus t, for example, okay? And the analogous piece from U. So as we discussed in the previous lecture, the residue has got to be a polynomial in t of finite order. Okay, I should have said this. This has got to go up to some s max at any level, because we can't have an infinite number of particles, right? We have to have a finite number of particles at any mass. So this is, even before getting to positivity, it's just a complete disaster. Okay. But if you take it, again, you try the same exercises, you always find it's the same difficulty. The reason we can't do it is with a finite number of particles, finite number of poles, we're trying to fix the high energy, fixed angle scattering, which is just some polynomial. But we can't, but if we're going to make it smaller than it is at high energy, in particular it has to be smaller than what it is if I take s enormous, making t small, but it can't be, because that sign is fixed to be positive. Okay, the only way it can be done is if you have minus signs, and that violates the rule. Okay. Okay, so this is interesting. Now, there is a formula that works. The formula that works is 1 over STU in the gravity case, delta 8 of Q, delta 16Q, delta 4P, multiplied by gamma of minus S over gamma of 1 plus S, gamma of minus T, 1 plus T. Oh, sorry. If I put the STU down there, it's gamma of 1 minus S, 1 minus T, 1 minus U, gamma of 1 plus U. And for the Yang-Mills case, there's delta 4 of P, delta 8Q over ST times gamma of 1 minus S, gamma of 1 minus T over gamma of 1 minus S minus T. Right. Those are the open and closed string amplitudes, okay, with maximal supersymmetry. In fact, maximal supersymmetry matters hardly at all here, because no matter how you compactify, whatever you do in perturbative string theory, the 4-particle amplitudes for gauge bosons and gravitons are very universal, especially for gravitons. Roughly speaking, because of all the KK modes and all the rest of them do not participate. They're not exchanged just in 2-to-2 scattering. So if you make a list of all the possible gravity formulas that actually ever appear, there are 2 formulas. There's the formula you get, this one, and the analog from the heterotic string. Okay? So there isn't a gargantuan set of possibilities that we can get, despite the fact there's a gargantuan number of ways of compactifying. They don't affect this leading 4-particle amplitude. Okay? But let's just focus on this one, where this is most certainly the only answers that we get. With maximal supersymmetry, it's totally unique. This is all we ever get in string theory. And we'll look at these things in a moment and see how miraculous it is that they satisfy these rules. Okay? And again, conjecturally, they're the unique functions that satisfy these rules. Okay? The more precise conjecture is that the only functions that satisfy, I'll say the very, very precise conjecture, let's say in the case of gravity, the only function of ST and U that at low energies looks like 1 over STU, okay, that's part 1. It has to look like 1 over STU, and it satisfies 2 and 3. The only function in the world is this one. Not quite. There's a tiny extra caveat, because I can sum this formula with different values of the string scale. See, I've tacitly put a string scale to 1 here. There's an S over M string squared, T over M string squared, U over M string squared. Okay? And there's a sort of a dumb thing that you can do just for 2-to-2 scattering. You can sum over different values of the string scale. See, since we're only talking about something good about the poles, if it's fine for 1, it's going to be fine for all of them. Okay? So there's a little ambiguity, which will presumably be removed if we talk about more things other than just graviton-graviton scattering or higher point scattering. But just with 4-point scattering, just for the clean question of, is there a function in the world that looks like 1 over STU at low energies? The claim is that every function that looks like 1 over STU is a sum over different possible MSs of that. That's a conjecture. Okay? But I want to give you an idea where this comes from. Of course, it comes from string theory. But how, from this bottom-up point of view, you would have ever guessed these gamma functions? Okay? And in fact, we can make a very simple ansatz, for what the amplitude should be, just taking some inspiration from what its low energy properties look like. And if we just follow our nose in 4 lines, we're going to get the gamma gamma gammas. All right. So this is definitely not a derivation because we're making a very simple ansatz, as you'll see. All right, so let's do the ansatz. So what I want to say is that I know I have to have an infinite number of particles, okay? But let's say, and I know it's a symmetric function of st and u, so let's just collect everything under some giant denominator. Right, I have some giant denominator, and so I'm going to have a product over a bunch of i's of s minus all the m squareds. Instead of writing m squareds over and over again, let me call them another variable, zi. T minus zi, u minus zi. Okay? And now what I'm going to assume is that the numerator has the sort of simplest possible form that mimics what we see here. Here we had a product of something in st and u. So I'm going to assume that the numerator similarly is a product of something in s, something in t, and something in u. Okay? Just sort of mimicking what we saw there already. So I want it to be a product over some other indices. I don't know what they are. Of, let's call it s plus xi. You'll see why I put the plus there. It doesn't matter. But t plus xi, u plus xi. Okay? Is that clear? All right. So this is the ansatz. Now immediately there's a crushing constraint that this thing has to satisfy, okay? Which we saw already. If I go on a pole in the s channel, let's say s goes to some particular zi star. Okay? If I go on a pole in the s channel, it had better be that the result doesn't have any poles in t. Right? It has to be a polynomial in t. In particular, it can't have any poles in t. Right? So let's see what happens. As s goes towards some fixed zi star, what I get upstairs, remember, u is negative t negative s. Let's remember that. So this would be negative t negative zi star. And so downstairs, I have a chock full of trouble. Just what we saw in our example. Right? Downstairs, I have a product of t minus zi and negative t negative z star I. Sorry, product over j, say, t minus zj, negative t minus zj, negative t negative z star I, negative zj. Okay?
The star is just a label.
Yeah, the star is just which pole am I talking about? Okay? And upstairs I have a product over a bunch of indices. I don't know what they are. So s is, I have put s to z star, so that's just a constant that goes out. Upstairs I have t plus xi, and u, remember, is negative t negative z star I plus xi. Okay? Sorry?
Why can't the numerator have different numbers?
Oh, I'm just saying it's a giant. I'm saying whatever it is. Since I'm assuming it's a function of s times a function of t times a function of u, I'm just assuming that it's the usual thing you say. I'm just specifying what it is by saying what all of its poles are. If you might have, for example, if you have a double pole, 2 of the x's would be the same. Okay, and then you'd get a squared there. Okay, so all of that is contained here. But you see something interesting. In order for these poles in t to cancel, it has to be that everything down here, like let's say some negative t, negative z star I, negative zj, there's a factor down here that looks like t plus z star I plus zj. It has to be compensated by some factor up here, right? And of course, I can't just compensate them by canceling everything, matching them 1 to 1, then I haven't done anything. So what I have to do is I have to choose the xi's have actually got to be the set of the xi's have actually got to be the set of all the possible zi plus zij's. And you see, if the set of the xi's are all the possible zi plus zij's, this works. These double poles are canceled. Okay? So now our new ansatz, and this is just from the most, we haven't even checked positivity, nothing, right? Just no double poles. Our ansatz is turned into the product over the pairs ij of this thing. S plus S plus zi plus zj, t plus zi plus zj, u plus zi plus zj, over just the product of the i's, s minus zi, t minus zi, u minus zi. All right? All right, now, so much for the massive poles. We have one more very important constraint, that at very low energies, this should match 1 over STU. Okay? So for example, if I look at the pole at s equals 0, so one of these things, one of the z's had better be 0. If I look at the pole at s equals 0, then its residue has got to be 1 over t squared, exactly. Okay? So I want to look at the pole at s equals 0. So what is the residue of the pole at s equals 0? It's going to be the product. So now at s equals 0, I'm going to have the product of t plus, let me call it xij, u, which is negative t plus xij, over, and downstairs, I'm going to have t minus zi and t minus zj. Okay? So indeed, in this negative t minus zj, negative t minus zj, the product over j. So if I pick out here the piece where zj is 0, so this is indeed 1 over t squared times the rest of them, right? So I have the product of all the t plus xij, negative t plus xij, over, again, the other way around, t minus zi, negative t minus zj, negative t minus zj, the product over all the j's, which are not equal to 0. So all the j's from 1, right? OK, now this is the right answer. 1 over t squared is the right answer. So it had better be that this whole mess up here, is 1. The only way that can be 1 is for every pole here, there has to be somebody, for every z down here, there's got to be some compensating xij up there. Right? So that tells you that if zi is a pole, zi plus zj must also be a pole. So that tells you that the set of all the zi's, what are the set of all the allowed zi's? The set of all the allowed zi's, have got to be some numbers such that if zi and zj are in this set, zi plus zj is in the set. What is that set called? The integers. 1, 2, 3, 4, and so on. Okay? Okay, they're all positive numbers. So we learn that the poles are at m squared equals an integer. That's the string spectrum. Okay? Sorry? That's the only set. Okay? That is the only set. You very quickly convince yourself, because if z1 is in there, 2z1 is in there, and by induction, everyone is in there. Right? So that tells us that the zi are all, or the zn are some n times some m star squared, some string scale squared. And we're done. Now we have our ansatz. Now we know what the amplitude is. Okay? So our amplitude is just the product that we wrote down. Okay? It's let me write it just in yeah, it's just, you can factor out the 1 over STU, and it's just the product over S plus I. Yeah, it's just this, S plus I, T plus I, U plus I, over S minus I, T minus I, U minus I. Okay. The product over all I equals 1 to infinity. Okay. And this is precisely 1 over STU. This mass is exactly gamma of 1 minus S over gamma of 1 plus S, gamma of 1 minus T, gamma of 1 plus T, 1 minus U, gamma 1 plus U. Okay? So if we make this very restrictive and simple ansatz, now, this doesn't tell us, remember, we have to have, I said that the set, I said that if there are poles, these had to be in there. We could have other things. I mean, I could multiply by other polynomials out in front. Okay? I could have other roots that were not there to cancel some of the bad double poles that we had. So at the moment, we could still multiply this thing by further polynomials in S, T, and U. Then if you take the more detailed version of causality that I didn't have time to explain, not just that it's polynomially bounded in S, but it has to be bounded by S to the 1, you discover that this thing already saturates that. Near T goes to 0, it's got to be bounded by S to the 2 in this example. And so any polynomial is already killed just by causality. Okay? So if you assume this factorized form, then it's very simple to see the gamma functions come out. Now, again, this is very far from a derivation, because why do we assume the factorized form? Okay? It is very, very far from a derivation. But what it really highlights is how magical these gamma functions are, right? That what they're doing is we haven't even checked positivity, right? They're even making sure that the most basic thing, that the residues are polynomials, is comes out right. Okay?
So what's the assumption you say that is far away from a derivation?
Well, the big assumption I made is that the whole amplitude is expressible as a function of S times a function of T times a function of U. The low energy amplitude looks like that, so you could take that as a hint that that's a good ansatz to begin with. If you do that, we derive the string amplitude plus a little causality, and we're done. Okay? But of course, it's a massive assumption to say that it should look like that. All right. So again, very far from a derivation, but it should give you a flavor. You can repeat the exercise for Yang-Mills, and you discover the analog for Yang-Mills. Yes. The natural numbers are the only set that's satisfied, and you can add other things. Okay, so that's what you could add other things to the set S, but in other words, here I'm assuming that the only zeros that I have upstairs are the ones that are needed to kill the double poles downstairs. Okay, and that gives me this rule, and indeed the natural numbers are the only set, because up to a constant. Because if Z1 is in there, 2Z1 is in there, so 3Z1 is in there, so 4Z1 is in there, and that means that everyone's in there. Okay, and no one else. So, sorry? The Z's need to be real because they're the location of the poles. The poles need to be on the real axis. We're making physical particles. Okay? Yes. No, so of course there's an overall scale in front of the whole thing. If there's a smallest Z, take the smallest Z. If the smallest Z is in there, 2 times the smallest Z is in there, 3 times the smallest Z is in there, so they're all in there. Okay? Okay? Okay. Yes?
You don't have to assume unitarity and say that emergence is
No.
somewhere?
We absolutely need it. We desperately need it. I mean, we haven't even checked unit. We've checked the most primitive aspect. We haven't even checked the positivity yet. The positivity is what we're coming to now. Okay. All right. So now let's do. Now let's actually check that. Let's check that having gotten these amplitudes, that they satisfy all the rules. Okay, very standard things you can do. You can see what happens at t, fixed t, if you go to very high s. Stirling's approximation tells you, for those gamma functions, tells you the amplitudes go like s to the some number plus t. Okay, so that's the famous Reggie behavior, and that's good. At fixed t, it's polynomially bounded in s. Excellent. We know that we get high energy fixed angle scattering, we get exponentially good soft behavior. That's good. So the interesting part is to check that it's positive. And while people wrote down these formulas, it was not for many years, 4 years after they were written down, that they were finally proven to be positive. This is in the way these things were done in string theory, both historically and in books. This is the famous no-ghost theorem of Thorne and Goddard and Brouwer. Okay, and a lot of books. This is sometimes treated as some sort of technical thing. Yes, you discover there's no ghost, there's a critical dimension, and stuff like that. But it's a little technical, and still doesn't have a very clean and conceptual proof. They have relatively simple proofs, but they're still it's still a little magical even after all of these years. And from my point of view, until the no-ghost theorem was proven, that string theory, even this dual resonance model, was not a physical theory. No one had any idea whether it actually propagated physical particles. It's an incredibly non-trivial fact that it propagates physical particles. So let's see that it does. And just to mix things up, so to let you have some fun by yourself and to use maybe a few of the things that you'll learn from Cliff's lectures in a slightly different context, I will let you by yourself do the analog of the exercise I'm about to do for gravity and for Yang-Mills. You take those gamma functions, you go on a pole in the S channel, and you work out what the residue is, and you see that it has a positive Gegenbauer expansion. But instead, I want to do it for the most primitive, the first string amplitude of all, just for fun, which is the Veneziano amplitude. Okay? So this is the magic of positivity. And let's see how it works for the Veneziano amplitude. So the Veneziano amplitude is gamma of negative s negative 1, gamma of negative t negative 1, over gamma of negative s negative t negative 2. Okay, so you can think of it as as again, it's an amplitude for an open string. There's you've stripped off a color factor. It's like pions. Of course, it's tachyons here. So it doesn't have a symmetry between s, t, and u, but has a symmetry between s and t. Okay, if you remember that the gamma function has poles at x equals negative n for n equals 0, 1, 2, and so on, then famously, if we look at this, there is a pole at s equals negative 1, right? The pole at s equals negative 1 is the tachyon. So at s equals negative 1, we have a pole, and it's a tachyon. Okay, but let's ignore the fact that there's a tachyon for this guy, but let's work out what is the residue on that pole. It's 1, right? The residue is just 1. There is a pole at s equals 0. And what is the residue of the pole at s equals 0? Well, we have gamma of negative t negative 1 over gamma of negative t negative 2, right? So what is that? It's t plus 2. Right? Remember, x gamma of x is gamma of x plus 1. So this residue is equal to t plus 2. By the way, what do we learn from the fact that there's a t plus 2? Who is propagating? There's a spin 1 particle, okay? Because there's something with a t there, and the t has a cosine theta in it. So there's a spin 1 particle. So we know there's a massless spin 1 particle here. Okay? Okay, but it's fine. Everything is okay with it. Now let's move on to the first level, which is s equals 1. So what is the residue at s equals 1? Now it's gamma of negative t negative 1 over gamma of s equal of negative t negative 3. And so this residue is t plus 2 times t plus 3. Okay? And in general, if we go to the residue, which is s equals n, the residue is t plus 2 up to t plus 2 plus n minus 1. Okay? All right. OK, but let's start at this first level. So we're going to learn something interesting already at this first level. So at this first level, we have a polynomial in t, which is quadratic in t. So there's a t squared. So already you know there's going to be a massive spin 2 particle. Okay? This amplitude is telling you there's a massive spin 2 particle. But our job is to expand this in Gegenbauer polynomials and see that they have positive coefficients. So let's do it. Let's remember the relation between t and cosine theta again. Remember, t in general was s halves minus 2m squared times cos theta minus 1. So let me call that cos theta minus 1. And here we're going on s equals n. Okay? So in this case, for the first case, we have s equals n equals 1. And m squared, we're scattering the tachyon, so m squared is equal to minus 1. So t itself is equal to what? T is 1/2 plus 2 times cos theta minus 1. So it's 5/2 times cos theta minus 1. 5/2 cos theta minus 5/2. And therefore, t plus 2 times t plus 3 is equal to 5/2 cos theta minus 1/2 times 5/2 cos theta plus 1/2, which is 25/4 cos squared theta minus 1/4. Okay? Now, our job is to expand this in terms of Gegenbauer polynomials. And now you have to remember, I told you, so what we see here is that we have a spin 2 particle and a spin 0 particle, right, in principle. Remember, g for a spin equals 2 in any number of spatial dimensions d, if I normalize it slightly differently than I did, is cos squared theta minus 1 over d. This was the first thing that had some dependence on the number of spatial dimensions. Okay? While for spin 0, it was just 1. So therefore, this is equal to 25/4. First, the cos squared theta, let me pull out a 1 over d. Cos squared theta minus 1 over d. I did that because now this is the g spin equals 2 in d spatial dimensions Gegenbauer polynomial. And then I have plus 1/4 times 25 over d minus 1. Okay? And so I learn that the spin 2 particle is fine, no problem. It's there with a positive coefficient. But if the number of spatial dimensions is less than or equal to 25, great. There's a scalar there as well with a positive coefficient. But if the number of spatial dimensions is 26 or higher, there's a ghost. Okay? So just the amplitude tells you that the number of spatial dimensions in this theory is bounded and has got to be less than or equal to 25. Okay?
Why f squared is minus 1 again?
Sorry?
Why?
It was the tachyon that we're scattering. Okay? So we're talking about the scattering of these tachyons. Okay? Right? So, and this is a general formula for the relationship between t and cosine theta, where m squared is the mass of the particle that you're scattering. Okay? Now, if you do this exercise for the other examples, if you do this exercise for the Yang-Mills example, you'll find d equals 9 comes out. Okay? All right, so you already see that it's non-trivial, that this is positive. You have to have a restriction on the number of dimensions of space. But now, let's say you go to the next polynomial, and the next one, and the next one. Is it obvious that they're all positive? Absolutely not. Massively non-obvious. Okay? In fact, we can easily work out what the claim is. Okay, so let me write it out. It's different. In other words, I'm going to just translate the residue polynomial into a function of cosine theta. And it's simple to write down the function for even level and odd level separately. Let me just write it down for even level for fun. Okay? So let's say the residue at s goes to 2n plus 1 as a function of cosine theta ends up just being the following. The product over I equals 1 to n minus 2 of x squared minus 2I minus 1 squared over 2n. Maybe I did 2n minus 1. 2n minus 1 squared. Okay? Well, sorry, where x is cosine theta. Sorry. This is cos squared theta. So, for example, we just saw the first one was cos squared theta minus 1 over 5 squared, right? The next one would be cos squared theta minus 1 over 7 squared times cos squared theta minus 3 over 7 squared. That will be at the third level. At the fifth level, it will be cos squared theta minus 1 over 9 squared, cos squared theta minus 3 over 9 squared, cos squared theta minus 5 over 9 squared. Okay? And so this is what it is. This is what the residue is in general. Okay, so the claim is that this function of cosine theta, that you can expand this as a sum over Gegenbauers with positive coefficients so long as d is less than or equal to 25. Okay? Right? So let's do, this is amazingly non-trivial. Okay? Let's actually show, so the simplest version of this, let's go all the way down to d equals 2 spatial dimensions. Okay? All the way down. It's true for any of it. We certainly go all the way down to d equals 2. Because in d equals 2, the Gegenbauer polynomials are very simple. What are they? What are the spherical harmonics on a circle? Just cosine s theta, right? So the absolute simplest version of this claim, which is already incredibly non-trivial, but which you could explain to a kid in high school, you could give them the problem, at least, is that this funny polynomial, the product of cos squared theta minus the product over I is 1 to n minus 2 of cos squared theta minus 2I minus 1 squared over 2n minus 1 squared can be written as a sum, just a sum over cosine s theta, cs cosine s theta. It's the most simple, straight Fourier expansion. Okay? With positive coefficients. Okay? Put this on the computer, try it in Mathematica. Yep, they're all positive. But there is no known proof of this statement other than all of the worldsheet formalism of the proof of the no-ghost theorem in string theory. It's fascinating. Okay? So this shows that and in fact, you can have a lot of fun trying to prove it without all of that fancy formalism. And believe me, we spent a lot of time trying to prove it without this fancy formalism. We've learned an awful lot of fascinating things about polynomials, which have these properties. And they have many, many remarkable properties that go well beyond that simple positivity of the coefficients. Okay? So it really seems very likely to me that there are some set of ideas that these positive functions are associated with, which are not so directly related to the worldsheet way of thinking about string theory. And that if we understood them, if we understood where these things came from a more invariant point of view, we could not only perhaps prove these conjectures. You see, what I'm showing you is how hard this conjecture is going to be to prove. Because even trying to directly check that the answer works without knowing about the worldsheet and all the rest of it is very non-trivial. Okay? But nonetheless, it's a clean, beautiful, well-posed problem. And I think wandering around in the neighborhood of these things and trying to find ways of proving them is going to be fruitful. So let me tell you something that let me give you a hint, an idea of why it is that this is very non-trivial. It's very non-trivial because these coefficients, while positive, start becoming exponentially small, okay, while always staying positive. And you know that that has to be the case for the following simple reason. Let's say that by the way, this continues to be true if you have this go all the way up to n minus 1. It's still true. But let's say you take it all the way up to n. If you take it all the way up to n, all you're doing is taking this giant polynomial and you're multiplying at the very end. You have these factors that are like cos squared theta minus 0.99999 something squared. And all you're doing is you're adding a last little thing, cos squared theta minus 1. Okay? The last factor here. The second you have the cos squared theta minus 1, the statement is false. It's false because if you put cos theta equals 1, on the left-hand side you have a 0. On the right-hand side, everything is positive. Okay? So it's incredibly sensitive. And in fact, you can't modify it at all. If you take the underlying residue as a function of t and multiply by some polynomials in s, here or there, s and t, you multiply by 1 minus 10 to the minus 10 s, 1 minus 10 to the minus 10 t. Whatever you do, there's a high enough level where one of those coefficients will go negative. Okay? So there are very sort of singular, remarkable things. Okay, so that's just, there's many more things to say about this subject, but mostly what I wanted to do in this last lecture is once again illustrate for the umpteenth time the tremendous power and constraints that we get from relativity and quantum mechanics. And in the context of weakly coupled UV completions, there's a very sharp set of rules that we have to obey. When you have theories with long-range forces, those rules are impossible to obey without an infinite tower of particles and an infinite tower of spins. I didn't prove that statement to you, but I made it a little plausible by looking at that phi cubed example. Okay? You need not only an infinite number of particles, but also an infinite tower of spins. With very simple, and we have existing formulas that work. These are the only formulas that we've seen in 50 years that work. It's possible there are other formulas out there. Okay? If there are other formulas out there, it would be stunning to know them. Absolutely stunning to know them. But it's also possible that these things are unique. And then that would tell us that whether we like it or not, some zeroth order, now it doesn't have to be that what UV completes gravity in our world is weakly coupled. But if it is weakly coupled, it has to look like this in some zeroth order approximation. That's, I think, an extremely interesting thing to know. And a little bit more generally, the same kind of ideas can be applied. They have less power, but there are other things you can do with them, and you can try to connect with other things that we know about QCD. You can try to use similar logic, just writing down consistent scattering amplitudes, really to return to the old S-matrix bootstrap program, and try to write down the amplitudes for glue balls in Yang-Mills theory. Okay? Now, for many years, people have said this is some kind of string theory. It's some kind of string theory. We can wait forever to discover the magical worldsheet theory that this is coming from, or we can just try to write down the answer. Okay? And this is, I'm mentioning this as part of the general futuristic aspect of what my lectures were supposed to be about, because you're already going to be seeing from Cliff's lectures how far we've come in eliminating the Lagrangian description from our description of gauge theories. Okay? And if someone told you 20 years ago there's some completely different way of thinking about how gluons and gravitons and everything scatter, where you never write down Feynman diagrams and Lagranges, none of that stuff is there, totally different structures show up, it would sound crazy, but it ends up being true. And those things that you thought were magical, wonderful, fantastic things like gauge redundancies turn out to be wonderful for what they're good at and obstructing you from seeing other things. Now, it's possible that the situation is possible. I don't know that it's the same, but it's possible that the situation is analogous with string theory. The analog of having all the gauge redundancy built into our description of physics is the worldsheet picture. There is a worldsheet picture for what string scattering is, and that loves gauge redundancy. Boy, it loves it. Okay, it adds an infinite amount more of it on the worldsheet, even than we have ordinarily in space-time. So it would be a little odd if we have found non-gauge redundant ways of talking about gluon and graviton scattering amplitudes, but forever we're slaves to ridiculously gauge redundant ways of talking about string scattering amplitudes. It seems plausible that there is a way of thinking about string scattering amplitudes that doesn't have a world sheet. It does not make the world sheet the star, just like with the program and scattering amplitudes, we have a picture that doesn't make Feynman diagrams and the point particle picture of scattering in space-time the star. And, well, it would be fantastic to know such a picture if it exists. And if it exists, it's possible that it will also help us figure out how to make sense of large NQCD. Okay? Instead of dreaming and waiting for this magical Lagrangian or worldsheet description to pop out of thin air, we'll have the machinery and the rules that tell us how to build it from the bottom up. Okay? So that's it for my lectures. We talked about the experimental future. We talked about various aspects of the theoretical future. But everything that I talked about was unified by strict adherence to data, right? Caring about new data with future machines, caring about old data, not messing up relativity and quantum mechanics when we try to make predictions for the future. And the fact that we're so constrained by data, both experimentally and theoretically, is what makes this business so amazingly exciting. And I hope lots of you have fun and perhaps develop some of these ideas in your own way. Thanks a lot.